So let me begin by stating the problem, which is of interest in many areas of physics, all the way from cosmology to all that, whatever. And its problem is very simply stated. You have a Hamiltonian with some time-dependent coupling. You prepare the initial state of the Hamiltonian as some equilibrium state, then zero temperature, some ground state. You want to figure out what happens at late times. It's of course intimately connected with questions of thermalization and various other things, much of which I will not discuss. In this talk, I will discuss a very specific case of this problem, where you basically take a conformal field theory and you deform it by some relevant operator whose coupling is time dependent. And the nature of the time dependence is something which we will take which approaches a constant at early and late times. The constant could be the same constant, different constants, depending on the particular situation which we use. And we'll always start off with the ground state of the system.
So the operator of breaks conformal invariance.
Of course. That's why I see this. Okay. So we call this quantum quench regardless of the rate of the quench. The rate of the quench is given by time scale, which I'll call delta t. This is like here to here or here to there. That's basically the time scale over which the coupling changes. And one of our aims would be, in fact, to study the behavior of various quantities as a function of that time scale. Now, for such protocols, some universal scaling behaviors have been known for a very long time. And the earliest known such scaling behavior was first proposed by Tom Kibble in the context of an expanding cosmology. Kibble was interested in the question that as the universe expands, it cools, and there are various scenarios of grand unified theories. You do have phase transitions. Some of them can be critical phase transitions. And during these phase transitions, typically all regions, because of the expansion of the universe, all regions of the universe are not causally connected, and the phase of an order parameter could be different in different regions, leading to defects. This is how we believe things like cosmic strings or monopoles or various objects in gauge theories are formed. And in this specific case, Kibble, who was investigating the possibility of cosmic strings being seeds of structure formation, asked the question, can I say something completely robust about the density of such objects, independent of much of the details of whatever grand unified theory I take? And so he came up with a very beautiful but extremely simple and naive argument, which actually had stood the test of time, as we will see. This argument was soon, not soon, 10 years later, was generalized by Zurek to various class of condensed matter systems. And in more recent years, the same argument and the same kind of mechanism has been generalized to quantum phase transitions. And the argument goes as follows. The regime which one is going to talk about in our particular context, as I displaced, is a regime when the change of this coupling is very slow. It's slow because compared to the scale, which is given by the overall constant in front of the coupling constant. There is a lambda naught here, which is some scale in the theory. In this case, this is the only relevant scale in the theory. So you want the coupling, the change to be slow compared to the scale set by the coupling. Okay. So if there was nothing interesting going on, this is the regime where we have adiabatic evolution. Adiabatic evolution would typically mean that the system behaves as if it were in some constant Hamiltonian at the instantaneous time. So instantaneous values of the coupling basically govern for you the behavior of the system. However, the interesting thing, of course, happens if this quench takes you across a critical point, and that's where conformal field theories also come in. Because when it comes to a critical point, regardless of how slow you start the coupling off, at the critical point, the gap is going to 0, so any rate of change becomes infinitely fast. What that means is that the system, so if you started out the system with some ground state, an adiabatic evolution would mean that the system would sort of continue to trace the instantaneous ground states, and when it approaches such a critical point, it falls out of equilibrium and the system gets excited, and you want to know whether there are some robust universal features which you can decipher in the subsequent time evolution of the system. So the scaling, so what Kibble and later on Zurek established some scaling relations of various interesting physical quantities, and these physical, the scaling relations are governed, as we will see, by some exponents, some equilibrium and near equilibrium critical exponents at that critical point. And the way the argument goes as follows is that suppose I have a coupling which near the critical point goes as some power of time. So the generic case will be r equal to 1. So there will be a time which is called the Kibble-Zurek time in this symmetric situation, which I call minus Tkz, which is determined by the fact that at this time adiabaticity has broken down. Once adiabaticity has broken down, there are very few techniques to study the time evolution of the system. So both Kibble and Zurek made the assumption, a very drastic assumption, the drastic assumption being that soon after this, the system just gets frozen to wherever it was. So the subsequent time evolution in this window was assumed to be diabatic. As we will see, there are slight improvements on this assumption. Assuming that, and assuming the fact, because the system is frozen, and the fact that
the system being frozen, you mean it just stays in whatever state?
That's right. So it's like a sudden.
Hamiltonian.
That's right.
But it's not the ground state.
No,
Whatever instantaneous ground state happened there. Okay. And the assumption that the only scale in the problem is the instantaneous correlation length at that time. And then you use some set of dimensional analysis to show that an operator, some typical operator which you want to measure, so some one-point function, goes as some power of that correlation length, which is the correlation length at that time Tkz. So this is just dimensional analysis. And then if there are some arguments, typically the analog of equilibrium scaling arguments pre-renormalization group, that the typical expectation is that you get, you don't have a stick or anything, right?
Yeah,
Oh, there it
there's
is.
a
Okay.
stick.
Oh, very good. Okay. That apart from this overall power, which is given by dimensional analysis, you can have a function, a slowly varying function of a time divided by the Kibble-Zurek time. There are improvements on this, particularly in recent years, on correlation functions, for example, which are supposed to behave in some similar fashion. And if you work out what this time scale is, the way you work that out is actually extremely simple and naive. It goes as follows. So near the critical point, the gap, I said, the coupling goes as t raised to the power r. So just by definition, the energy gap of the system goes at whatever that raised to be z times nu. Nu is the usual correlation length exponent. Z is the dynamical critical exponent, and the time of adiabaticity breakdown is just determined by what is called the Landau criterion, namely that the time rate of change of the gap becomes large or same order as the square of the gap itself, as appears in adiabatic perturbation theory, and just plugging this thing just gives you this answer. And once you get that answer, you also get what the correlation length is, and so you, if under those assumptions, you get these scaling relations.
And if you did all of this, but without demanding that you go through a critical point, you just have some region where you change your coupling.
Yeah, except that if the only place where the nature of the critical point appears is that the way the gap scales as a function of time, and that's where the critical phenomenon is in those exponents. So anywhere, if you had a situation where adiabaticity broke down, that would be the case, but it wouldn't be typically universal unless you're near a critical point. I should say one thing, that apparently, and I'm not an expert on this, people apparently do experiments on systems in order to test this kind of idea, and even though generally there is, from what I understand, is that the general nature of the phenomenon has been observed, there are sort of controversies of whether precisely those kind of exponents are actually obtained. But nevertheless, the interesting thing is that this is actually accessible to experiments. It is accessible to experiments, but as you can see that the arguments which lead to this kind of thing don't go too much better than this. There is no analog of the conceptual framework of a renormalization group for strongly time-dependent phenomena, which actually provides justification for the kind of assumptions which we make. There's some recent progress along those lines, but it's really at an elementary stage. And this is one of the reasons I got interested in this area. As we will see, we'll try to see whether we could get some insight by mapping the problem by using ADS-CFT techniques.
So what happens when the coupling actually goes to the value where it would be a CFT? At that time, is there a sudden change in things again?
If it goes like that,
yeah, at the center point t equal to 0 in this picture, that's when it actually becomes the exact CFT.
that's right.
And
Well,
it's
still time dependent. There's no conformal invariance. Yeah.
But there's no sudden sharp peak in anything or changing. There's no marker at that point that is being special.
As we will see, for example, when you just hang on for a moment, I'll see there is actually a little bit of a marker because there is a certain violation of conformal invariance because of the time dependence, and that actually carries signatures of these exponents. There's another extreme which you can think of, which I'll call an instantaneous quench. So instantaneous quench is a sudden jump of the Hamiltonian from one value of the Hamiltonian to another value of the Hamiltonian. And for example, I could take a massive theory away from the conformal point, and this here the word quench is really used in the dictionary sense. They just quench it suddenly to the critical point. In this case again, there are a very impressive set of papers by Calabrese and Cardi over the past several years, where they made an argument that the state of the system, of course, this is really a instant change. So the state of the system doesn't change because Hamiltonian changes just too quickly for anything to happen. So of course, what is the ground state of H0 is not the ground state of H1, and that's where the interesting physics is. And you want to figure out how to understand the nature of what I'll call the quench state, which I've denoted by psi naught. Okay. So you want to understand how is this quench state related to standard states which you can form in the conformal field theory, which has happened after t equal to 0. So what Cardi and Calabrese argued is that in general, what one would expect is that for long distance behavior of quantities, this state can be written in terms of an operator which is the final Hamiltonian. This is the CFT Hamiltonian times dimensionful number, which I'll call tau naught, acting on some boundary state. Now, this is a little bit of a technicality. I don't want to go into that. There's some class of states of the conformal field theory. If the and this quantity tau naught is actually related to the inverse of the gap of the initial gap. So if the gap was infinitely high, you know, like it sort of, it's going to, and it quenches down to the conformal field theory, this would be just frozen down to the boundary state.
And this boundary state depends on what my initial H naught
Yeah,
is.
it does depend on the initial H, because there can be lots of boundary states, of course, right?
And so is this argument rigorous, or what's the nature of this validation?
The top it's, there's no proof of this argument. It's case by case. In fact, the last talk we had some talks by Gautam Mandal, which actually showed cases where this doesn't hold, in fact. But in a large class of systems, it does hold. The general sort of argument is that so when you quench from a state, from a Hamiltonian which has some large gap, and you quickly quench it down, so then the system would get excited, but you wouldn't expect all possible excitations, in a sense. That it would sort of, the excitation should be sort of capped off by the mass gap itself. So this is why this tau naught is roughly 1 upon the mass gap. That's what this factor does. This is like the least relevant operator in the theory. So and so if you go to further refinements, you'll have the less relevant operators which appear.
Sorry, but why cannot psi not be any state that you want, and it could be any state?
No, this is the state which results from starting out. This is the ground state of this Hamiltonian.
Yeah, but I can always put some, you give me some state, I can.
You can. So you could start with some other state of the theory, for some general squeeze state of the theory, and then there are analogous statements about that. This statement is only about the ground state.
No, I mean, if you give me some arbitrary state, I can always make some Hamiltonian that this is the ground state. So why would you some restriction on this? I know this can be.
No, this is a statement of starting with some Hamiltonian which is characterized by a gap, and you start with the ground. You have the ground state of that Hamiltonian. You are expressing that ground state of the Hamiltonian in terms of the states of the conformal field theory. And what this says is that for IR quantities, many of the details of the Hamiltonian are not going to be important. What is going to be important is in fact the gap itself. Your question?
Yeah, I think just to restate his question, he's kind of reverse engineering it. I've got a conformal field theory, pick an arbitrary state in conformal field theory, and make up a Hamiltonian for which that is a ground state.
Is it possible? Is it possible to have a local Hamiltonian?
Well, maybe.
Yeah, you could revert if you get into a local Hamiltonian. Yes, you could invent. So you're saying the Y is particular class of states.
Y is particular class of states.
I don't know. It just works out. It's. I mean,
Maybe it's true.
well, I'll tell you the words which Cardi and Calabrese use. The words are like that. If I have if I do such a quench and get to a conformal field theory, I mean, if you start with any object and look at very, very long distances, the words are, it should flow to one of the boundary states, and this is the correction to that boundary state. Don't drag me on this. I'm not going to talk about this, neither do I understand this very well. Okay. For specific Hamiltonians, I can show how this happens, but I think I don't know of a general argument. But if you accept this argument, that it does follow, there are interesting set of universal results. For example, if you calculate the 1-point function of an operator which is not conserved in time, so that it actually has a time evolution, so it relaxes down to typically some zero value at late times, you can ask how fast does it relax, and this is the relaxation time, tau naught divided by the conformal dimension. So what this tells you is the relaxation time itself, there is nothing universal about it. There are many, it depends on the microscopic details of the Hamiltonians. But if you could find two operators with two conformal dimensions and calculate their ratios, that ratio is universal. So in that sense, it's sort of interesting. The third set of scalings, which I'll talk about, is actually something which got discovered when people started looking at this in the ADS-CFT correspondence. And I'll describe pretty soon in detail what kind of setup this is. This is a kind of a new scaling which relates to time scale, which is much smaller than the inverse gap. So in a sense, it's fast, but which is much larger than any UV scale in the theory, like the cutoff. So it is not really an instantaneous change of the Hamiltonian. A really instantaneous change of a Hamiltonian would be a change at where the time scale is short compared to every other scale in the theory. So it's not that. There's some intermediate regime, and as we will see, this is the regime which one can deal in renormalized quantum field theory. So that's what we will do. In that regime, expectation value of the operator which is being quenched.
So the general theory could have lots of very particular structure between the gap scale and your UV cutoff scale. So why would you expect any universal behavior? Is this a certain class of theories which sort of, so to speak, have basically
When I
two
come to
scalars?
the demonstration of this, maybe you will see where this comes from. It's like, it's saying that there can be lots of things, but it's saying that delta t is small compared to all physical scales in the theory. So in that process, it's the fastest. Okay. That's where it comes from. This quantity goes as some power of delta t, which again only dictated by the conformal dimensions and the dimension of the quantum field theory. And similarly, the energy density has a relationship which of course has to satisfy some kind of Rogers theorem. Now it turns out, this was a little bit puzzling in the beginning, and I'll sort of try to understand and resolve that puzzle, because if you look at this expression, you'll find that if delta is greater than d upon 2, this blows off. And one might wonder what happened, because as delta t goes to 0, you might imagine that it actually becomes the previous case, which is an instantaneous quench. And there are lots of examples known where these are well controlled. So what is this limit? And a lot of my talk will be about that. And what we will in fact argue is that these kinds of conditions are in fact completely general. It has nothing to do with ADS-CFT correspondence or holography or particular this model or that model. Under the assumptions which I'll clearly state, these results actually just follow in a very simple fashion.
That's interesting. This was not known to the condensed matter feature before they got to the
ADS-CFT.
So it's a genuine.
Actually, it's a genuinely new result. I mean, yeah, it was first found in holography, and then we showed that it's a general result. Okay, so let me just remind you of the general setup for how we use the ADS-CFT corresponding to study these quantum quenches. So, as this is the standard blah-de-da about ADS-CFT, it provides a relationship between large N quantum field theories and deformations of conformal field theories. And the only thing that we are going to use about that is that for every bulk field, there is an operator. Like if there's a scalar field, there's a scalar operator. If there's a gauge field, there's a current. There's a metric perturbation corresponds to the energy momentum tensor. And if I do an asymptotic expansion of these bulk fields near the boundary of ADS from the behavior as a function of this coordinate z, which is the ADS radial coordinate, I can identify what are the deformations of the conformal field theory and what is the response to that deformation. Okay? So basically this is an example for a scalar field expanded for small values of z. This delta is the conformal dimension of the operator which is dual to that scalar field. So this has one integration function of the bulk equations of motion, which you would typically identify with exactly the space-time dependent coupling constant of the theory, and in which case if you calculate this object by solving the differential equations and imposing suitable regularity conditions, this will give to you the expectation value of the dual operator. And that's about the only thing we are going to use, at least for this talk. So I should tell you that this problem of quantum quench therefore translates into a classical bulk problem with a time-dependent boundary condition, which is a difficult problem to solve, but it's a problem which can be formulated very precisely. You have to solve a partial differential equations with some given initial conditions and given boundary conditions. It's of course infinitely better than trying to formulate the problem in a strongly coupled quantum field theory, which is a dual. So hopefully we learned something. There's a large literature on this subject. One of the earliest uses of this kind of thinking was actually to make models of space-like singularities, which I'll not talk about. There's been a lot of understanding of properties of thermalization of strongly coupled field theories by doing such a thing. But in this talk we will not talk about this, but talk about this critical behavior which I just mentioned. So what do we need to in order to map this problem of quantum quench across a critical point? We need to identify a bulk theory which is dual to such a critical point. We need to impose some time-dependent boundary conditions on a bulk field that is dual to a relevant operator at that critical point, and we want to need to calculate the response. So these are the three steps. You can do a lot of things with it. I'll do the simplest thing of having homogeneous quenches, so things are only dependent on time, they do not depend on the space coordinate of the field theory. So these are the papers. And let me just give you one particular example. So this is something which we have looked at in a variety of situations. They are very similar, and the lessons we learn are also very similar. So let me just stick to one particular example which actually illustrates the main points. The bulk theory is a theory of gravity. There is a Maxwell field, so that means the boundary theory has a global U1 current, which is conserved. There is a charged scalar field, so that means there are charged operators under that global U1 in the field theory, which is minimally coupled to this and which has a potential, which I have just chosen like that. The potential can be anything you like. In fact, we will see how things do depend on the potential. One of the directions of the boundary, so the ADS has a radial direction and a boundary direction. We'll take one of the directions to be compact. So for such a compact directions, interesting things happen in the bulk, and the geometries can be of various kinds, as we know. So we will take one of the regime, which is in fact the simplest regime, where if you have a compact bulk direction, the compact boundary direction, what it corresponds to in the bulk is an ADS soliton, which is roughly an object which looks like this. This is the circle, and the boundary is smoothly capped off to a smooth size in the interior. This is a solution with the scalar field input to 0. And on top of that, what we are going to do is to have a constant value of the time component of the gauge field. What this would correspond is a constant chemical potential for the corresponding charge on the boundary. So that's clearly a solution. Now recall that this is the asymptotic behavior of the scalar fields. So even with a vanishing lambda of t, so that means if even with a constant, even when the source itself is vanishing, phi equal to 0, even though it's always a solution of the equations of motion, you got to ask whether the solution is stable or not. And what it turns out, and this is what's the result of these people here, and the result is that there is a critical value of this chemical potential mu beyond which this solution is not thermodynamically stable anymore. So as a result, what you need to look at is, for mu greater than mu c, is there any other stable solution? And it turns out that with suitable non-linearities, the non-linearities can come from various things. In our case, we can look at a situation where the non-linearity is produced by the scalar field itself, but the non-linearities can be produced by the coupling of the scalar to the background gauge field. Actually, it doesn't matter where the non-linearity comes from, whether provided it's of a particular kind. It turns out that there is actually a non-trivial solution with a non-trivial response. What that means is that even that, so I wrote E of t, but forget about the time dependence for the moment. So basically there is a non-trivial solution with a zero source, but which is regular in the interior. So what that means is that there is an expectation value of the dual scalar operator O, because this part is non-zero, and it is with a given potential, bulk potential, it's not very hard to calculate how does the expectation value depend on the chemical potential itself. You can analytically calculate, and the result is something like this. If it's some power, if the leading power of the potential is like, the arguments are pretty much like mean fields here, nothing more fancy than that, then the expectation value goes as this particular power when the source is 0, and if I tune the chemical potential to its critical value, it scales with that external source with a power which is 1 upon n. So this is very much like, in a magnet, how the magnetization goes with the temperature or with an external magnetic field. Let's first study what is called an extreme probe approximation. Now there is a coupling in the theory, a bulk coupling, which I call lambda. This coupling controls the self interactions of the scalar field. And if you look at the way lambda, and then there is another coupling which is the charge, and there is a third coupling with the gravitational constant. You can choose a regime of these couplings where the basic physics is essentially given by the non-linear differential equations of the scalar field itself. So this is the lowest order approximation. It's very easy the reason why you want to start with that is it's very easy to just look at a single equation rather than try to solve a coupled set of equations. In some suitable redefinition of coordinates and fields, which is not really important, the equation has a structure which looks like this. So let me just point out the main points of that structure. This object, this coordinate u is actually a time coordinate. It's a null time coordinate. It's like an Eddington-Finkelstein coordinate in the bulk. Okay. We want to do a causal physics, so I think it's good to choose ingoing Eddington-Finkelstein coordinates. This coordinate rho is some version of the radial coordinates. It's analog of what we call tortoise coordinates if it were a black hole. Okay. This is an operator which is a differential operator which only involves the rho. So rho is the analog of the ADS radius coordinate. It goes from 0 to some value rho star, if you wish. These are the equations, not very important. So this part gives a time dependence. There is a powers one time derivative here, there is another time derivative there. The right hand side is completely, there is no time derivative on the right hand side. So that's just, if you were to solve the equilibrium problem, you set the left hand side to 0. This operator D, it turns out, is an operator which is like a Schrodinger operator in an external potential. I didn't draw the potential. The potential as a function of rho looks up roughly like this. The depth of this potential is some, which in here actually depends on the mass of that scalar field. And you know, this is just the linearized part, so it doesn't depend anything on the coupling itself. Okay. What you can show is that if I take this part of that operator, this is just this part, and this is just some constant which came from the chemical potential. This part has always a positive spectrum. That means if I just took that potential does not have any bound states. If I add on a chemical potential, what it does sort of brings this thing down. So at some value of the chemical potential, there will be a threshold bound state for that potential. The threshold bound state will be the onset of instability of the problem. This is quite standard in this game. This is exactly what happens for holographic superconductors and things like that. Exactly at mu equal to mu c, that exactly the place where the zero energy threshold bound state appears, this operator has a zero mode. What that means is that, see, beyond mu equal to mu c1 I called here, there is a solution with the right hand side set to 0 with trivial boundary conditions and regularity in the interior. Okay? There's something special which happens when mu equal to mu c, is that the linearized equation has a non-trivial solution. Because typically for arbitrary values of mu, it's not going to happen that you have a zero mode of that operator which is normalizable and which is regular in the interior, but that's exactly what happens. That's again one of the important features of this phase transition. By the way, since there is a charged operator which is acquired in an expectation value, this is sometimes called the holographic superfluid. Okay. So one of the ways of doing quantum quench in this model, which is easy to do, there are other quenches which you can perform, is to tune the value of the chemical potential to the critical point and introduce an external source lambda of t. So this is the coupling which couples to that charged operator, and have a function of time which goes like this. So some positive value to some negative value. Okay. So the critical point happens when lambda is 0 and mu equal to mu c, which is exactly at this point. And this is exactly the type of protocols we have been talking about. Okay. Now, in this setup of the problem, all you got to do, well, not all you got to do, it's a hard thing to do, but you have to solve a partial differential equation with, of a function which is a function of rho, which is a space-like coordinate, and time. And under the condition that, now the geometry which we started out with in the bulk is a ABS-Holiton geometry. That's a gapped geometry. So it is a gap in the problem which relates to the radius of the circle at infinity. So if you are going to change things at a rate which is slower than that gap, you would, as you would expect, you should be able to solve these equations of motion in an expansion in time derivatives. That is the adiabatic expansion in this problem, because we have, if you were to do the quantum problem, it will be a quantum adiabatic expansion as in textbooks, but here it has become easy. It's just a classical differential equation which you are solving by a WKB approximation, if you wish. So that's exactly what you would do. And as you would imagine, as you approach this point t equal to 0, when it crosses the critical point, this time expansion in derivatives with respect to time is going to fail. And just looking at the equation, you can figure out where does it fail. It's again it's a very simple classical differential equation analysis, and you can estimate where that it fails. and you get a result which looks like this. This is for a phi-4 potential. You can do it for, you know, many different potentials and just illustrate the result for the phi-4 potential. So this is like the adiabatic regime has stopped here. After that, you have a tough set of nonlinear equations to solve. You don't know what to do. One thing you know is that that equation doesn't, the solution of that equation has no power series expansion in inverse delta t, is it? Because a power series expansion in inverse delta t, which is the rate, the Taylor expansion is basically the time derivative expansion, and that has failed to converge anymore. What we will find, however, is that in the regime where it is in the critical regime, and I'll show you what the critical regime is, there is a new expansion which emerges. So that critical regime is a regime where I can approximate lambda, but just by its behavior near t equal to 0, which in this case I have just taken it to be the linear in time. And again you can repeat the analysis with some power of time. So a good way to analyze the problem is to split your bulk field into a source piece, because you have to put those boundary conditions and something which has trivial boundary conditions, and you expand this remainder piece in terms of eigenmodes of that operator D. So it's like the spectral decomposition of the field, reducing a PDE to an infinite set of ODEs. Okay? Lambda 0. Which lambda 0?
In the top line.
Oh, lambda 0 is a constant. Yeah, that's the overall scale in the problem. So what do you find by looking at this and by suitably rescaling fields in a suitable fashion is that what emerges in this region is again an expansion in large delta t. It's a series expansion, but not in integer powers of delta t. It's an expansion in some fractional powers of the range. Again, for equilibrium critical phenomena, things like this happens and sort of like at the root of how non-integer critical exponents emerge. Here it is sort of happening as a property of the bulk differential equations. I don't know how to translate that in terms of the quantum field theory itself. In particular, in this case, this expansion is in some power 2/5. That 2/5 is intimately related to those powers which appeared in the failure of adiabaticity. Now recall, there is a special thing which happens at mu equal to mu c, and the special thing is that there is a zero mode of that operator d. So if you look at this equation, that equation which we are going to solve, where is that equation? So I have done a spectral decomposition of this field psi in terms of the eigenfunctions of that operator. So clearly something special is going to happen when that operator itself has a zero mode. And what you find by looking at those equations is that to lowest order in this expansion, what we find is that the dynamics is completely dominated by the zero mode. Okay? So there is one single mode of the bulk scalar field which is basically carrying with it all the leading order time dependence in this slow quench level. So you first started off with a partial differential equation, you reduced it to an infinite set of ordinary differential equations, now you get one ordinary differential equation only for that zero mode. It's quite trivial to look at the features without you don't have to even solve that equation. You look at the features of that equation and the scaling property of the solution just falls off. So once you have that scaling property, then the ADS-CFT correspondent tells you that the operator has a scaling property with SDFT. Okay. So this is the crux of the argument. And I don't have a general proof that this is always going to happen, that we've looked at many models and it seems to happen. So there's some general lesson here. I think one of the lessons which I would like to take away from this is the fact that typically whenever you have scaling in any phenomena, what this means is that there is a decoupling of scales in the theory. It is that decoupling of scales which is sometimes very difficult to understand in a time-dependent background, because the background itself being time-dependent couples high energy scales with low energy scales. But here, effectively, in that critical region and only in that critical region, this doesn't happen outside that critical region. Only in that critical region, again there is some kind of decoupling where the zero mode had a decoupled dynamics from all the higher modes. And given the fact that the dependence on the ADS coordinate is like a scale in the boundary theory, it is roughly speaking some kind of decoupling of scales in the boundary theory, which is giving that scale. Yeah.
This is equivalent to rescaling the metric by a power of t. It's a conformality, because you say that lambda is t to some power, so the Hamiltonian is so the action is the conformal theory plus t times O.
Okay.
If you say that the metric is t times the metric, so you do like a wide rescaling of the metric, you will get just the t in the O.
So this is which metric are talking, the boundary metric or
Yeah, the boundary metric. So you
the
have
boundary
this
metric.
theory,
So
there
if
is
the
no
operator is like an energy momentum tensor, that's what it would be.
But that is conformally flat, so you could reduce the flat space by.
If it is the yeah, but this operator is not the energy momentum tensor. It's some other.
No, suppose you have f squared and then t to some power times O.
Yes, but it depends on which operator it is.
Yes, suppose you take the metric and you multiply the metric by t to some power. The f squared remains the same and the t goes away in this
Oh, is that from the square root of g?
Yeah. And the dimension of O.
Yeah, if there are no other, I mean, if it's just a scalar operator with no other powers of the metric, that's what it would be. Yeah, that's right.
Then you don't have t anymore. Or?
No, you do have the t because you have the
You have an
power. Yeah. Okay, so I just gave you the analytic argument. We did some extensive numerical solutions of those equations, and this is what a typical profile of the order parameter of the operator O, which is being quaint looked at. You start with some value. We started with some value of the source, so O already had an expectation value, and then it sort of, if it were done, suddenly it sort of flipped to the other side. So of course it just goes to this, and it has oscillations, and it sort of, maybe at late times it's going to settle down or something. The thing here you note, which you cannot see very clearly here, is that if it were following an adiabatic evolution, then this in equilibrium, the expectation value of that operator, if you had just a constant coupling, would be that lambda raised to the some power, some 1/3 or 1/4 depending on the universality class. So at lambda not equal to 0, this equilibrium value is 0. It's of course offset by some amount, and that's the thing which you can plot very carefully. So this is what I plotted. Now the expectation value of operator at time equal to 0. This is the departure from, in fact, an adiabatic evolution. Is plotted against the log of the inverse of delta t, and you see this very nice, scaling behavior, which is almost perfect.
O is a complex order parameter. You say it's actually charged under.
Yeah.
E1.
Right.
And so why are you taking the real? Why don't you take the norm?
It has very similar behavior.
If you
Both the
take
real and
norm,
imaginary parts have pretty similar behavior. Okay,
And that oscillation is just in the numerical plot you showed for the real part.
Right.
It's just part of a phase.
That oscillation is just because, so far as the equation is concerned, there's kind of a restoring potential. It's been kicked off a little bit from its equilibrium value, and the restoring potential is causing that oscillation. So it's like a harmonic oscillation around that.
What sets the period? What sets the period?
What sets the period is the relative magnitude of the quadratic part of the quadratic term in the field itself compared to the kinetic term. Okay.
Can we do does this hold only for adiabatic quenches, or can we do for in the fast quench as well? Like when it
No.
is falling?
What I have shown here, it's quite important that you take a quench rate which is slow compared to the initial gap.
So can't we take a fast quench and maybe decompose it as a Fourier series and then take the sum of that will be a sum of several adiabatic quenches, right? So we take each adiabatic quench and then sum the whole thing to get the final fast quench limit. The sum of
Maybe in
adiabatic.
a linear problem that might work, but I think in general that kind of thing is going to work.
But we can decompose any function in
You
a
can
Fourier
decompose
series.
any function. The question is that once you put that into the equations, whether the solution will not be a sum of the individual things. Yeah.
So back to this oscillation in the final state. So doesn't that mean that there's kind of a component of the superfluid order parameter after the quench, which is an eigenstate of the number operator? If you're saying that's an interpretation of that oscillation in the end.
You're saying so that's the.
So there's kind of a coherent. It looks like a substantial fraction that's a coherent
Right.
phase oscillation.
That's right,
in
yeah.
five, So is that something also interesting? I mean, in this system, you're saying you end up in after the quench in a state, and what fraction is in the condensate phase?
Could be. I'm looked at that. Could be. Of course, most of our interests are in that critical region right after the quench.
No,
We
I
haven't
understand.
looked very much at late times when these approximations also break down, the zero mode dominance also break down. But that could be an interesting question. I should say that I've shown the results for the leading order in a probe approximation. It turns out it's not that important. We actually very painfully worked out the back reaction of this, both to the gauge field and to the gravity, and things work in a pretty similar fashion. It's not in the critical regime, things are not that different. Of course, as a result, you get some new scaling relations of the charge density as well as the energy momentum, etc. But I don't think there's much of a big deal about that. There should be other scaling quantities which are very interesting, and one of the things which we are concentrating now at the moment is the way the entanglement entropy of a region depends on the rate of quench. This is something which in the condensed matter literature I don't think hasn't been looked at very much. There are a few examples which are quite indicative, but as we know, ADS-CFT gives you a very nice and compact way to calculate entanglement entropies even in a time dependent situation. So I believe that you're going to learn something out of this. I'm not exactly sure what we are going to learn about this. How are we doing in time? We have half an hour left.
Yeah,
Yeah.
a little bit more.
Okay. So let me now go switch gears and talk about the regime of fast quench. This is the work of Bushel, Lehner, Myers, and Van Niekerk. What they did a detailed numerical solution. They took the simplest ADS-CFT, in various dimensions, and they turned on a source. They actually turned on a source with some compact support. So it's actually basically turns on at some point and then it reaches a constant at some other point, and they calculated the response of that source. And what they found, first numerically, and then there was an analytic argument, bulk analytic argument of why such a thing would happen, is basically what I showed you earlier, that the expectation value scales as some power of delta t, the energy density scales as some power of delta t, and this equation always has to hold. It just follows from, it's a word identity, it follows from time translation, broken time translations. And this result seemed to be pretty robust in the holographic setup. It's valid not only when you start off with the ground state, namely just pure ADS. Even if you do a thermal quench starting with some black hole, basically the same kind of thing happens, so long as the quench rate is fast enough, and that's where it's important that the quench rate is fast compared to all other physical scales in the world. And there was a bit of confusion in the beginning, because as I just pointed out, that in the limit of delta t going to 0, these objects seem to blow up for certain dimensions which are greater than d upon 2. So you might wonder, is this looks pathological? Could it be a property of these very special strongly coupled field theories which have gravity duals? There aren't that many of them, so maybe those strongly coupled theories have this property. Whereas most of the literature about very fast quenches do not deal with such things. They deal with transverse field Ising models and quite normal quantum field theories. Maybe it doesn't happen for those things. So so we thought that that's probably not the case, and in fact what we will find is that this is in fact a very general result in any deformed conformal field theory. So this is some work which I have done with Rob Myers and Damian Galante, and some work which is in progress with my previous student added on Vitarka Das Krishna Sengupta, which is in progress. And we'll start with the most trivial thing you can imagine, just the opposite case of a strongly coupled field theory, a free field theory. Okay. So let's do a free bosonic or a fermionic field theory with a time-dependent mass. And the whole strategy is to find mass functions where the problem can be exactly solved. And by exact solution, I mean you can calculate all quantities exactly and analytically for any value of the quench rate, and then we're going to look at these expressions and carefully study the limit of the fast quench. And as you'll see, we'll learn a few things. So this is the warming up. So this, I just give you some mass profiles for these things which can be exactly solved. By exactly solved, what I mean is that you can made a mode decomposition of the field in terms of solutions of the, in this case, the Klein-Gordon equation. For the Dirac equation is the Dirac equation, where you know what these things are. And these things look like that. So I think you don't want to look at it anymore. But all you know is that this is some hypergeometric function which you can put it in mathematics, and mathematics can calculate what the values are. Okay. Of course, being a time-dependent situation, we are if you look at these profiles, these are all going from one constant value of mass to another constant value of mass. So there are being a second-order differential equations, there are lots and lots of solutions. So you got to tell me some initial conditions of the modes which you start out with. And by the nature of the problem, we are going to choose these in modes. In modes are modes which behave as positive frequency modes at infinitely early times. Okay. So this is the Heisenberg picture state. which we are going to consider, and we are going to compute simple expectation values in this Heisenberg picture state. One of the things we would compute is, of course, the expectation value of I square, which is the operator which is being quenched. It's like people call it a mass quench, and that, of course, is trivial once you know what the solution of your mode equation is. This is what the answer is, and quite trivially, this, of course, is divergent, because in field theory, everything is divergent because you have a sum over momentum modes. But normally we know how to deal with this situation. If it were a situation with a constant mass, this would be taken care of by normal ordering. You just order the operator, which it's phi square is a composite operator, so you can order the operator such that all the E's appear to the right of the A daggers, and then you're done with it. So in general, what you would do, what this would amount to, is to take this object and obtain a renormalized expectation value, which is obtained by this, by subtracting off by a set of counter terms. Of course, a good way of doing it, and that is what we did, is to take the action and add counter terms to that action, and once you have, this action has to be written in some generic time dependent mass and generic background, and taking suitable derivatives of that action, you get various expectation values. But at the end of the day, this is what it amounts to. This is how you renormalize composite operators even in interacting field theory. But now, because the background is time dependent, these counter terms will depend not only on the instantaneous value of the mass, but by its very derivatives. It is like the way you renormalize a quantum field theory in curved space-time. There again, you have to introduce counter terms. The counter terms typically involve curvature invariance of the background space-time, and curvature invariance, of course, are derivatives or metric of various kinds. In this case, you would expect that you would get time derivatives of matrix of the mass various kinds. When you are doing a quantum field theory in curved space-time, there is a principle which sort of tells you what kind of counter terms you would have. They are governed by the general covariance of the background metric. You cannot have some arbitrary derivative of the metric. You must have things which are made out of curvature and its invariance. And so you might wonder, if I just put in some arbitrary, time-dependent couplings in a given action, is there any simple way to figure out what these counter terms would be? It turns out that these counter terms are exactly reproduced by an adiabatic expansion of phi square. And doing that actually teaches you something. So let me tell you what do I mean by an adiabatic expansion. This is the exact answer for phi square, because these are the exact modes. But instead of solving the equations of motion exactly, I could have solved the equations of motion in a WKB approximation, as is done in textbooks. So you introduce some function, it's like the Hamilton-Jacobi function theory. This is the wave function. It satisfies some equation which is solved in a time derivative expansion of this function. Right? And once you have solved up to some whatever your desired order in the time derivatives, you plug that in and obtain the value of phi square. This is what I mean by the adiabatic answer for phi square. So the claim is that if I look at this and look at the high momentum behavior of this integrand, that will cancel all the divergences which are contained in here. And it solves up. So this is an example of the kind of what I was just talking about. This is an high momentum expansion of that integral. As you can see, it has various time derivatives. It has powers of momentum which depend on the dimensionality. And as you increase the number of dimensions, which you will notice is also increasing from the CFT point of view, the conformal dimension of the operator which is being quenched, more and more of these terms become relevant and contribute to the ultraviolet divergences and have to be removed. Now, it sounds a little bit funny because adiabatic expansions are always good for slow changes in parameters, Whereas from the very beginning, I am saying that I want to look at fast quenches, which are very fast changes, changes which are fast compared to all other scales in the theory. So why does it work? What is the relevance of this? And there it is important to realize that this rate is small compared to, in this case there is just only one scale, so it's just the gap of the theory. It's small compared to that, but it's always large compared to the UV scale of the theory. And that's why we are doing a renormalized quantum field theory, because we want to look at scales which have nothing to do with the UV scale of the theory. Towards the end of the talk, I'll do some lattice models where this is not the case, and we'll have some interesting lessons to learn. But in this regime, it is quite clear that the high momentum behavior, which is the UV of the theory, that doesn't care whether your time scales of the physical process is faster or slower than some other physical scale, because the UV physics is completely insensitive to what happens there. This is why this procedure actually gives you all the correct counter terms to remove the divergences in the theory.
So this is adiabatic in the sense of the UV cutoff, not gap.
Yes, that's right. Yeah, because you're trying to look at the UV of the theory, so the gap is completely there. So this is an example of the kind of responses which you get. The various curves are for various different rates. These are just numerically plotted using Mathematica, and this is an example of the time, the kind of time dependencies of the energy which you could get. And this is for this very particular profile, which goes from some value of the mass to zero mass. Now, if you look at these analytic expressions, you find that the drastic simplifications occur when you take this limit. This is the limit when m times delta t is very small. I don't have much of an intuition why it happened at this moment, but I mean, we will see in a general setup why there is a simplification. And what you find is a set of nice analytic formula which tell you the leading answers for the response as functions of the derivatives of the mass function. And as you can see that each time derivative is like delta t raised to the power d minus 4. In this case, there are logs for even dimensions, and there's special formula for d equal to 3 and 4, and they're all consistent with a general law up to logs of delta t raised to the power d minus 2 delta. Okay. And as I said, I just give you a specific example of a particular protocol, but this is quite general. You can do all kinds of things. So, and this is again some impressive numerical results which Damian pulled out, but very perfect scale. So we found a scaling behavior which is true for a class of very strongly coupled field theories, which are holographic duals, and the same scaling behavior for trivial weakly coupled, the weakest possible coupled field theories, which have not gravity duals, but maybe, I don't know, some higher spin duals or whatever, but not interesting from the bulk point of view. So you might wonder that maybe the result is actually quite general. So let's try to pursue that. So this is what the setup is. You have a CFT and you have a coupling with some operator, which I'll take to be a relevant operator. And let me take the coupling something of this form. There is an overall scale times some function, and the only property of that function we will use is that it goes through some constant at early and late times. It has some excursions. Excursions are all order 1. They don't go off to infinity or do some strange things. And that's the only thing we're going to require in this for these functions. And we are going to look at the time scales delta t, which are small compared to everything else in the problem. They're small compared to that. I think answers your question. If there are many scales, it's compared to the initial lambda, to the final lambda, whatever excursions you have. It is really the limit of a very fast question. Good. And let's start calculating the expectation value of the operator by using perturbation theory. Okay. So what do we get? The first term which we get is the expectation value of the operator at the initial value of the coupling. Okay. It's not a CFT expectation value, but expectation value with some deformation of the CFT, which is characterized by lambda naught. This delta lambda is like the overall, I just subtracted out lambda naught, whatever you get, that power that comes out is I've just called that delta lambda, and it's multiplied by an integral which has the function of time which you have put in, and a retarded Green's function with the 2-point correlator of the operator O in that deformed conformal field, because that's what it started off with. Okay, so this is just the commutator of two O's multiplied by a theta function at lambda equal to lambda naught.
This is an expansion of what? Delta lambda over
Delta
lambda
lambda.
naught over lambda naught.
Will come to what you will find that, see, normally this kind of expansion is not very good. I mean, they are infrared divergences, but here we'll see that this actually makes sense. Okay, we'll immediately see what this is an expansion of. I'm also going to assume without proof that all these things can be properly renormalized in the theory. So namely, you can get rid of the UV junk by properly renormalizing the theory. Consider, for example, the first term. The first term has an integral over time which is 0 to some time, the time at which you are measuring the response, and an integral over all space. So normally these things are dangerous because of the integral over all space, particularly if you are starting with a CFT. However, suppose I ask a limited question. I ask a question that I am not going to look at the response at arbitrarily late times. I am going to look at the response soon after the quench has ended. Now this is a causal Green's function. What this means, that if I measure the thing at time t, it is going to get a support. This space integral is going to get a support only over the past light cone of that point, right? So all these integrals are over bounded intervals, which are of the order, I've written capital T here, which are of the order of capital T. So if I am going to measure it at t equal to delta t is the time when the quench has ended, then since I am dealing with renormalized quantities, so basically the both of the space time intervals which appear in the integral are at most of size delta t. Okay, so that gets rid of any kind of potential IR problem, because it's an integral over a compact region. Recall, by assumption, the scale delta t is smaller than all other physical scales in the problem, which includes the scale which is associated by the initial deformation of the conformal field theory, which is given by lambda naught. So therefore, for such a case, if I look at Green's function, whose distance scale is much smaller than the mass scale in the theory, it's basically a conformal field theory Green's function. Okay, so the leading order result will be a conformal field theory answer. So as a result, what you have, I can write the expansion. So the only scales in the theory are the scale which is set by the relevant deformation and delta t. This, in the limit of fast quench, everything else has gone away. So I can write that result as an expansion in a dimensionless coupling, and this is what the expansion is in. is an expansion of delta lambda with a suitable power of delta t, which is raised to the power d minus delta to make it dimensionless. Okay? So it's a power series expansion in G, possibly multiplied by functions which are slowly varying functions of t upon delta t. So this will be the form of my full answer. Okay. I don't know how to calculate these things, but what I do know that in the limit of G very small, it's only the first term that is going to contribute. It's important to note that this result by construction in the limit we are considering is completely general. It depends only on the properties of the conformal field theory in the ultraviolet, and it doesn't depend on what happens later on. The reason why it doesn't depend on what happens later on is because we are only measuring it right after the quench. Okay? That's why the Itard-Green's function doesn't have any information of the final value of lambda. So in the limit of small g, which is the fast limit, is the first term that contributes, and if you just open up what g is in terms of this, plug that in, you get that scaling law. So in a sense, the linear response is becoming exact in this limit.
What happens for large capital delta? Large, don't you?
This one. So that's the next slide.
Oh, okay.
So why is there a divergence in our free field result? We saw divergence when delta t goes to 0 for d greater than 4. In any conformal field theory, there will be a divergence when capital delta becomes greater than d upon 2. That's a question you want to ask. Right? Okay. The rest of the talk is about that. One comment I would like to make is again to reiterate the fact that we are dealing with renormalized quantities, right? So therefore, delta t can never be really taken to 0. You should not compare the delta t going to 0 results of these renormalized quantities with those of an instantaneous quench, which actually require a quench rate fast compared to all scales in the problem. This can cause a bit of a confusion. For example, when you have even dimensions, we found that there are logs, you need to introduce a renormalization scale. So that made us wonder, why don't we try to look at this problem in terms of explicitly ultraviolet finite objects, because there you don't have any confusion of counter terms, scheme dependence and all that, and let's see what happens. So here is one object which is ultraviolet divergent free, which is insensitive to the UV. You compute the energy density at late times now and subtract from it the energy density of the system, of that system, had it been in the ground state of the final value of the coupling. Okay? So this is a measure of the excess energy that is being produced. Presumably it's of some very physical consequence. Here is for the free bosonic theory, for example, this is a general expression for this energy density. And the reason why this is ultraviolet finite is because we saw that if I just looked at the energy density itself at some given time, it can be rendered UV finite by subtracting counter terms, which involve that value of mass at that time and time derivatives of the mass. But since we are looking at very late times, all those time derivatives have gone to 0. And the thing which only depends on the mass will be already captured by this particular quantity. So that's why the UV scale has completely decoupled out of this. So this is just another set of formula which just explicitly shows why this is UV finite. So here are some answers for the free bosonic theory. I've compared that answer to the answer what you would have got by doing an instantaneous quench, namely starting with, in this case I think we started with some mass and then went to 0 mass. I forgot which one it is. You can do it for any of those quench limits. I've compared that answer for the delta t going to 0 answer of the smooth profile with that of instantaneous quench. So what you find is that for low dimensions, this quantity actually goes to a finite limit as delta t goes to 0. Okay, and that formula which I showed would have shown that it goes to 0 as delta t goes to 0. It doesn't. It goes to a finite limit. And for large dimensions, namely when the conformal dimensions of the operator, perturbed operator, are large, they actually diverge in the limit of delta t goes to 0. At the same time, if you look at the answers for the instantaneous quench, that this finite part, of course, agrees when it is finite, whereas in those cases, the instantaneous quench itself gives infinite answers. So it is sort of consistent with that limit. These results are for free fields. We have indications that similar things would happen for general interacting theories. The kind of arguments which I just presented, we don't have quite a proof yet that for the excess energy this is how things are going to scale, but we certainly believe that this scenario.
Can you summarize the physical argument as to why we will diverge once again? Why energy density diverge for this?
When you try to take that limit?
Yeah.
So I think it just if you do something very suddenly, then somehow you sort of injected probably an infinite amount of energy. I mean, it depends on the dimensions, because I think there must be a phase space argument why for low dimensions it is actually finite, but for high dimensions it actually.
Can you just think of it as taking all the, let's say, we change the mass, all the harmonic oscillators for each Fourier mode, we just change their potential function, right?
That's right.
So we've gone to a squeeze state for every oscillator.
Absolutely. That's what happens. That's what this Bogolubov coefficient is, right?
So I'm simply computing the Bogolubov coefficient energy all the way up to the scale set by delta t, and whatever energy that is when delta t is very high. So all the Fourier modes k all up to 1 over delta t, how much energy they get when getting squeezed is the amount I get.
See, essentially that's where the phase space appears. See, for each harmonic oscillator, if you compute what's the change of the energy of the harmonic oscillator, if you do a sudden change of that thing, it's that finite. It's there's nothing infinite about it. So it's a sum over harmonic oscillators which is giving you this infinity, and so it's a phase space.
So depending on how many dimensions that will oscillator, and that's what
That's right. Another UV finite object is a correlation function of this basic field at a finite spatial separation. Okay, so if I of course have a finite separation, I mean it is not going to look at the UV properties of the theory. So I'm going to look at the equal time correlation function at finite separation. I'll be done in about 5-10 minutes. Okay. What one would expect is that for large enough separations and late times, that this should agree with the results of instantaneous quench. And the reason basically is as follows. If you look at the momentum space Green's function, and we look at the high momentum limit of that momentum space Green's functions, the infinite rate limit of that does agree with the high momentum limit of the instantaneous quench. So it's a question of the integration, right? Now, if I look at a separation which is large enough, large compared to the scale which is set by the quench rate, then you don't have to integrate all the way to infinite k, right? So it doesn't matter that in the finite k region there is a difference between the two. Okay? So very large separations you would get an agreement with the this was part of the reason why you would look at, nobody actually is ever going to do an infinite quench, right? Infinitely fast quench. But if you look at the IR quantities, it really doesn't matter whether you do a very fast one or a slow thing. So that's what you would expect, and that's indeed correct. So this is, for example, the difference of the correlation with that of an instant quench, and you can see they all nicely go to 0 as the separation goes to 0. The separation becomes large. The most interesting behavior, however, appears at finite times. And this is where you start seeing the scaling in these UV finite objects. This is a representative plot of the correlation function at a time which is just after the quench at delta t, with some fixed quantity subtracted out for plotting this thing. The different colors are the correlation function for different values of the spatial separation. Okay? So I think these blue ones, so as you go up, right, you know, this one is like a very small separation, this is slightly larger, and all the way to very large separations. Other way around, right. This is large and that small, right? This is large and that small, and what you notice is that when, and this, what is being plotted here is delta t in a logarithmic plot. Okay, so what you notice is that there is some change which is happening when delta t basically becomes of the order of r. So at r, which is much larger than the delta t under consideration, then the dependence on delta t saturates. You know, the answers become independent of delta t. Okay. But there is a regime where from delta t of the order r to some region where there is this nice scaling behavior with delta t itself, and that scaling behavior, which is the scaling of the overall coefficient of the two-point function, is exactly this d minus dl, and that's what this verifies.
A few slides back we have seen this divergence property of this delta epsilons at d equals to 4, logarithmic
There is a
divergence.
log there, yeah.
Isn't it the same thing when we try to calculate the rotation functions, and there's a logarithmic divergence for the self energies of the theory with certain energy, and they are similar to the logarithm, right?
Yeah, it's just for d equal to 4, what happens is that the operator, what happens for d equal to 4? For d equal to 4, 2 times delta just becomes equal to d. Okay. It's still a relevant operator, but it's just the trace square operator becomes marginal, basically. Pi 4 becomes marginal. So it's a signature of that, actually. That's why
So
it's a log.
by looking at that, can't we say that this is the same thing that we do in the Wilsonian energy, that we integrate out up to the length scales and find out the divergence dies out. That this delta t is order of the r, is the sense that same kind of a renormalization factor.
I don't think there's anything like that. It's just a simple fact that when you look at distances much larger than delta t, we only got to integrate to momenta up to 1 upon delta t, and that's what the reflection is. And that's the regime where, I mean, it's at for momenta which were much smaller than the UV cutoff, but still bigger than your scales. That's the regime where renormalized quantum field theory works. So it's exactly that. This is a very trivial theory. There is no integrating out, doesn't give you anything here. Okay. You have some questions? No. So we established I described a very well-known result which has been known since the 1970s of scaling behavior for slow quenches. Then we investigated something which we learned recently, which is about fast quenches, a different kind of scaling behavior, but nevertheless looks quite robust. So it might be of interest to look at a situation where you can switch the whole regime from slow to fast. For renormalized quantities in a field theory, we did that. I'll not give you the details of that, but it is this beautiful plot. In order to look at something like Keeble-Zurek, it's best to have a situation where you go from a gapped phase to a gapped phase with some with crossing some critical point in the middle. So for the bosonic theory, you can sort of free bosonic theory, you can do that for a quench which sort of looks like this, from massive to massive. But for a fermionic theory, this actually is easier because you can do a mass function which goes like this. The sign of the mass of a fermion has no physical significance. So this is actually in terms of the gap for this fermionic thing is still like that. So that's good enough. So that's an easy thing to do. That's what we did first. And this is a plot of the expectation value of psi bar psi for all values of delta t, all the way from very small values to pretty large values. And what you see is that there is a regime which is this, in this particular case, that this fast quench scaling goes as 2 minus d. There is another regime which is exactly Kibble-Zurek, and this is measured at a time which is a little bit before t equal to 0, and at very large delta t, it is still in the adiabatic regime. So the leading answer becomes again independent of delta. Okay. So the things move on quite smoothly. Finally, let me come to, we have been to a situation where we actually have a physical system with a finite cutoff. So far we have been talking of continuum field theory, so we are not accessing any of the physics at the scale of the cutoff. But for real systems, that might be of interest, because real systems do have a cutoff, and you might want to see how things do depend on cutoff. In particular, as I had emphasized, for quench rates which become of the order of the cutoff, we expect a kind of saturation with respect to the quench rate, because we should be able to approximate it by a sudden change of the Hamiltonian, and it could be of interest to see how this actually happens. So we decided to do this for models which are of interest for various condensed matter systems. And the simplest thing, if you open a book, what you find is a transverse field Ising model. Okay, so you do a transverse field Ising model with a time-dependent transverse field. And as is well known, this is a one-dimensional Ising model with a transverse field. This can be mapped into a theory of a single Majorana fermion with dispersion relations which have cosines and sines rather than q squares and stuff like that. So there is a Dirac equation which looks like this, and you're going to find a g of t for which the Dirac equation can be solved exactly. Okay, it's easy to find that. We managed to find it. Okay, so you blah de da. This is one example where you can solve this thing. So you can solve this thing, and you calculate something again which is interesting, the expectation value of sigma 3, which is related to psi bar psi. And here is a beautiful result of that calculation. This is again a plot of a log of delta t and then the psi bar psi, which is the expectation value of sigma 3. And again you see, we don't quite understand the saturation values very well. We sort of know that it should saturate. Signaling is sent to saturate for small values of delta t, and then there is a fast smooth. In this case, it's 1 plus 1 dimension. Our result predicts a log. That's what this log is, and this is the Kibble-Zurek value. So it sort of smoothly goes over to Kibble-Zurek. We also expect this to saturate at very large delta t's, but we haven't seen that yet. So I think it gives a pretty consistent picture. As I said, we don't completely understand the saturation. We've also done the thing for an interesting two-dimensional model for reasons I don't understand. It's considered to be interesting. It's what's called a Kitaev model on a honeycomb lattice. Anything that can be mapped to Majorana fermions is actually good. This one gets mapped in a slightly more non-trivial way. So it's an exact quench protocol for the Kitaev model, which is a little more complicated, just mathematically from what I just presented. But nevertheless, it can be done. We haven't completed that work yet. And I'll just finish with the sense, with the hope that maybe this is of some real use. So who knows? Thank you.
expectation of the scalar operation and energy density
Mhm.
as the same scaling property?
Yeah. So that actually follows from the word identity. The leading behavior would be quite similar. See, the word identity, or Noether's theorem in this case, tells you that the rate of change of the energy density is of some sign. The rate of change of the coupling times the expectation value of the operator, right? So, but you know this thing. So one time derivative gives you 1 power of delta t, but that's sort of compensated for the other thing. That's basically it.
I was wondering that maybe energy density might be proportional to scalar scale, something like that.
No. So it's because this just follows from the fact that the Hamiltonian is some constant Hamiltonian plus some lambda t times operator, some integral of space. So you just take the agency of that. I should also say that for these free theories, of course, there's a whole host of things which I didn't present, which you can do there. You can see consistent scaling properties of the higher spin currents. You can construct an infinite set of higher spin currents in theory and calculate those, and there's nothing, no big deal about that. Once you understand one of them, you sort of basically understand the rest.
Intermediate is computed in the fast using or any variable.
The entanglement entropy. I only know a couple of papers which calculate the entanglement entropy for that in a time-dependent setup. That's what you are asking. And those, I think, are done for slow quenches, not for fast quenches. Entanglement entropies are notoriously difficult to calculate even in free theories. So, but these calculations are numerical calculations using words which I don't understand, words like time dependent, density matrix. But there are sort of very interesting patterns in those results which I would like to understand. But I don't understand.
This non-energy energy which you got when you quenched in some cases, if you were doing it in the ADS context, for example, then the large n, the n of the large n, that should also come in the answer sort of linearly because every degree of freedom would get excited by the degree.
That's right.
So can one see that there is an n dependence in that situation?
So I think when you calculate it holographically, what you're actually calculating is the expectation value of the T mu. You actually divide it by a factor of the Newton constant there. So from the field theory point of view, you're actually calculating 1 upon n squared times energy density. So it does scale with n squared, the true energy density, which in the bulk is the Gn which appears in the action, but those things are with that factor taken off.
Let's thank Sumit again.